Hello, it's Keith here, and this is lesson 23 of the ChibiAkumas series of my Z80 programming tutorials. This is going to be a bit like the last time where we looked at the RLE encoder. This time we're going to look at compiled sprites. So even if you're not really interested in ChibiAkumas, if you've not heard of compiled sprites and you want to learn more about them, I think this is going to be quite interesting to you. And we're actually going to look at the compiled sprite builder that was used to make ChibiAkumas, and I'm going to show you how you can use it to make a quick compiled sprite and use it in your own program potentially. So firstly, we need to discuss what a compiled sprite is, because they're quite unusual. Now, if you think of a normal sprite, as in your character sprite or an enemy sprite, some background, things like that, they will typically work in the following way. You'll have a piece of code which will actually work out where the sprite needs to be drawn, and then it will read the data that actually makes up that character. And there may be some kind of X flipping to make the character face the other way, or some clipping if the character's half on the screen, but generally speaking, the code will read in the data and then draw it to the screen. Now, a compiled sprite, technically speaking, is different. A compiled sprite is a piece of assembly code which directly draws the image onto the screen. There's no real data as such. Now, I say technically because my compiled sprite generator does actually create some bitmap data because it needed to save space, and then we'll go into that in just a moment. But essentially, it's a piece of machine code that is dedicated to drawing a single image, and the reason we do this is it's very, very fast. Far faster than an RLE, far faster than a conventional sprite, because there is no data, and the compiled sprite generator that I wrote is, and most of them will, is designed to work out the fastest way that this image can be put onto the screen. Now, the disadvantage of a compiled sprite is it tends to be very big. Now, a 16 kilobyte screen without any optimization was actually ending up bigger than 64 kilobytes in some cases. So I've had to do a variety of tricks to make it more efficient. Now, in this lesson, we're just going to look at compiled sprites as a concept, and I'm going to show you how to actually use the compiled sprite builder in Aku23 editor. But next time, we're going to have a look at the code that the Aku23 editor produces and the optimization tricks that I use to try and save memory, and generally what the compiled sprite is actually doing to get the image to the screen so quickly. Now, first of all, I want to show you ChibiAkumas episode 2. And here is the last boss battle. And we're going to have a look at the compiled sprites in action on the 256K version of the game. Now, you'll see that there's this background here and the game's currently paused, but when I unpause the game, you will see that it's actually a series of 8 frames of animation that are creating a pre-rendered 3D effect. And even though we're completely redrawing that background every single frame, the game is actually running pretty fast still, and that's because the compiled sprite is so fast, it's faster than any other way of drawing that screen. Even so, I did have to do an interlacing effect just to keep it as fast as possible, because this part of the game is pretty intense still. So anyway, let's see that in action now, and let's see. So here you can see we're playing the game as normal, and I'm dying as normal. But the point I'm making is that the compiled sprite is able to do an animated background on the 256K systems. It did take a lot of memory, so it's not available on the, I think it's not even available on the 128K. There are some other compiled sprites, there's some very large other backgrounds and animations, but that animation is only available on the 256K systems, and that's because I'm effectively using about 128K of extra memory for those compiled sprites. Each frame, I think, was about 8 kilobytes, so the 8 frames were taking about 64 kilobytes of memory, and there were a few other frames as well in there extra for the compiled sprites for the 256K. But as I say, that's what the kind of thing that we can do, and it's something that only compiled sprites could do. If we were doing that by memory copying with an LDIR, it wouldn't be fast enough. So that's the concept. Let's have a look at how we can generate them. So here's Aku23 editor. Now, Aku23 editor wasn't what was used to create ChibiAkumas episode 1 and 2. Both games did use compiled sprites. It was a compiled sprite at the end of the game in the first game, version 1.66, and the original. The brick wall background on the Necromancer stage, that was a compiled sprite. In episode 2, the last boss battle used a lot of compiled sprites, and there were also some on the anti-vampire machine. So there were quite a few compiled sprites in episode 2. This wasn't the program that was used to do the original episode 1 and episode 2, but this program was used to do version 1.666. Now, the program can create compiled sprites for the Amstrad CPC and also the ZX Spectrum. It cannot do them for the MSX. The reason for this is the MSX can't get direct memory access to the video memory fast enough for compiled sprites to make any sense. There's no way for us to do any Z80 tricks to get graphics data to the screen faster than the VDP can do it. So we're kind of stuck there, but that's why that system isn't covered. Now, when it comes to creating a compiled sprite, we just need a sprite in memory, so I'm using this sample one here again. Now we're going to go here to CPC, Sprite Compiler, and add one. this will add a single sprite to the buffer, and you can see it's saved to the clipboard here. And now if we just go here and we do a paste, we've now pasted the data that's in that buffer. Now we also have options for add one diff. This will add a difference layer between the last sprite and the current one, and then you can layer them on top of each other. This saves memory, and it can also be used for transparency. And there's a clear option which will clear all of the compiled sprites currently in the buffer. Now we need to make some changes to this to get it to work from our example today. When I was doing ChibiAkumas, I was saving these to disk files and then loading those into memory, but we're not doing that in this case. So we're going to take this org statement out here, and we're going to change this to a call. We're going to make this return back to basic once it's done. Now, if you remember, basic on the Amstrad CPC needs the BC shadow register to be preserved. So we're going to do an EXX, push BC, pop BC, EXX, and a return. Another thing you'll notice is we're at the far left-hand side of the screen here. We need to be tab indented on things like Vasm. Now, this example won't work on Vasm. Unfortunately, when I wrote the Sprite compiler, I didn't use Vasm, and so it doesn't have that more proper coding style that Vasm requires. So if you're going to use this, I'm afraid you're going to have to use WinApe. But unfortunately, because I'm planning more multi-platform games now, I'm not planning to use compiled sprites again. So I can't invest the time in actually sort of fixing that limitation that it only compiles with WinApe. Now, another thing we're going to have to do is we're going to have to disable the enable interrupts from the end of the code, because otherwise the interrupts would enable and that BC wouldn't be correct. So there we go. So we've just made that change as well. And all of these changes are documented on my website, so if you didn't catch them here, please just go and check them out, and it will show you what changes you need to make if you want to do the example we're doing today. So we can now just compile this. So if we just press F9, you can see we've built without any errors. And now if we do call and 8000, you can see we've now drawn our picture to the screen, and we immediately came back. Now, it's important to notice that was actually faster than the RLEs, but in most cases this will be faster than any other possible way you can get the graphics to the screen. In a worst case scenario, it may not be much faster, but it's really the most optimized way you can do things. So that's how we can get our CPC sprite to the screen. Now let's just clear that out here, and this time we're going to do a spectrum sprite. So what we're going to do is we're going to clear out all of this code here, just delete it out. And this time we're going to change the build CPC directive here to a build ZXX directive. So we're going to build a spectrum sprite this time. And we go to ZX and we go to Sprite Compiler and add one here. Now this again has saved the compiled sprite to the clipboard, but this time it's of course in ZX Spectrum format. So if we just paste this here, and then once again we need to make a few changes, and once again they're all documented on my website here. So first we're going to take this org statement out. Again, we're going to make it return to basic. So what we do is we change this to a call and put a return in. But if you remember, the ZX Spectrum needs the IY register to be preserved. So what we're going to do is we're going to do a push IY here and a pop IY here, and that will preserve that IY register. Now, if we try and compile this, we will probably see something quite interesting will happen. We've got an error message and we've got an undefined symbol. Now, when the Sprite compiler operates, what it's doing is it's working out what it needs to do to make the sprite faster, and then it's defining the bits of code that it needs to run that. And unfortunately, there's clearly a limitation that it's forgotten to create one of the commands. So we're going to make it manually. So if we just have a look at multipush DE40, now what we need is a version that does 31. Now, all of these commands are very straightforward. So all we need to do is we need to take the 40, and we need to change this to a 31, and that will fix the problem. It's a very small problem. It's just the case that while the Sprite compiler works in most cases, occasionally it makes a slight mistake. So we've just had to manually fix that, and now we've got no errors. And so what we're going to do now is we're going to run ZX go TRD to load the program we just compiled. And there you can see we've got our ChibiAkumas sprite here, and we've returned back to basic here. So that looks like it worked just fine. Now, the important thing to understand is that was just black and white, but the Sprite compiler can do color. It's just I didn't put any in. So that's not a limitation there. But as you can see, we're able to do the sprites to the Amstrad CPC or the ZX Spectrum. And as I say, it's effectively a trade-off version. It's faster than any normal sprite, but it's not quite as fast as a pure compiled sprite. because there is some bitmap data in there, and the reason for that is the file size would have been too big to load into the 64K addressable memory in most cases, and it would have certainly been too big for what I wanted to do with regards to my game. And that's because with those backgrounds for the last boss, I needed to fit them into 16K buffers to be able to actually draw them to the screen while the game was playing. So there we go. That's a brief overview of what a compiled sprite is, how we can actually create some using Aku Sprite Editor, and how to show them to the screen, and the few tweaks you'll have to make for Aku Sprite Editor. Next time we're going to have a look at the actual content that Aku Sprite Editor creates. Of course, I need to point out there were many other sprite compilers out there, and of course they'll all work differently. I'm not saying this is the best way to work. This was just the way I came up with, and maybe if you're feeling adventurous, maybe you'd like to write your own sprite compiler. I found it a lot of fun, so I'd certainly suggest you consider it if you want to. Anyway, thanks for watching today, and goodbye.